KSP, which really just stands for equilibrium constant solubility product. And we call Ks that are related to the solubility of some insoluble salt KSP. And the main reason for that is that there is no denominator when we write the K, because these are solids and it doesn't go into the K expression. So simply the K expression for this is silver concentration times chloride concentration. Hence the name solubility product. The solubility because this is dissolving, product because we have multiplication over here, and product is another name for multiplication. So let's do a quick couple of calculations on here. Let's assume that we have some silver chloride in solution or in a container, and there's some water above it. So let's calculate how much silver will dissolve, or what the concentration of silver is in that solution. Now, you might have been told that silver chloride is an insoluble salt. And for the most part, that's true. This equilibrium is not very product favored. In fact, it's very reactant favored. Hence, the K for this reaction is only 1.77 times 10 to the minus 10. That's very reactant favored. And we tend to say, oh, that's an insoluble salt. But of course, a little bit of it will dissolve. Let's calculate how much that would be. So we're going to pull out an ice table, and we're going to say that we don't have any of this to start with, or this. So we start with 0 of each of those. And when silver chloride dissolves, we will make X amount of silver and X amount of chloride. And if we add that up to complete our ice table, that I didn't write ice over here, but you guys know what we're talking about. There's the equilibrium mixture. And let's put that into our K expression. So our KSP is 1.77 times 10 to the minus 10. And that will equal the silver concentration times the chloride concentration. So we have that. Both of those are X. X times X is X squared. So to calculate what X is, we'll take the square root of both of these. And X in this case will equal 1.33 times 10 to the minus 5. Now, in this case, this is the concentration of both the silver and the chloride in the solution, because this is a 1-to-1 ratio salt. There's 1 silver for every chloride. Now, something that might happen is we could have a solution that already has either silver or chloride in it. That would be adding a common ion into the mixture. Now, going off of Le Chatelier's principle, we should know that if we add one of these in, let's say chloride, because that's more typical. Let's say we add some chloride in here. Well, Le Chatelier's principle says that we would shift some back to the reactants to use up some of these products. And so less of the salt would dissolve if we have another source of chloride, say from sodium chloride. So if we had something like a little bit of chloride in the solution, we should expect that less of the silver chloride will dissolve and the concentration of silver will go down accordingly. So let's see what happens when we, instead of having a solution of pure water, we have a solution that contains 0.1 molar sodium chloride. Now, 0.1 molar sodium chloride will have a concentration of sodium of 0.1, but that's not the important ion here because there's no sodium up here in the equation. It will also have 0.1 molar chloride in the solution. So let's write a new ice table down here where we instead have 0.1 molar sodium chloride in the solution too. So we still start off our silver the same way, but over here our initial concentration of chloride is 0.1. The rest of the ice table is the change is similar. We're going to dissolve X amount of the silver, and if we do that, X amount of chloride will be added there. And so 0 plus X is X, and 0.1 plus X is, well, 0.1 plus X. Now, let's take this and plug it into our KSP expression right up here. So in this case, we'll have 0.1 times, or X times 0.1 plus X. So let's write that. X amount from there, 0.1 plus X. And again, this equals 1.77 times 10 to the minus 10. Now, some of you may recognize that this is a quadratic equation, and we could solve it using a quadratic formula, but I'm here to say that's not necessary. Just like we have ignored the minus X on a lot of our acid-base calculations, we could ignore the plus X here. And we could make that assumption even based off of looking at this X here. You'll notice that this is 10 to the minus 5. Now, if I add something that's 10 to the minus 5 to 0.1, it won't make much difference. Certainly not a significant difference based on the number of significant figures I have here. But, again, remember, Le Chatelier's principle says that if we add some ion in, less of the equilibrium will shift over to the reactant side, and less products will be made. So X should be much smaller than what we've already calculated. And it was already small. So we could ignore this plus X right here. And that will simplify our calculations, because at that point, it's just 0.1 times X equals 1.77 times 10 to the minus 10. And that should leave us with an X equal to 1.77 times 10 to the minus 9, if I did that math correctly. Now, this is the concentration of silver in the solution. The concentration of chloride is simply just 0.1, because adding 1 times 10 to the minus 9 or 2 times 10 to the minus 9 to 0.1 is not going to make a significant change in its value. So, this is how to do some KSP calculations using an ice table. And also what would happen if we added a common ion into the mixture. Actually, I think that a lot of times adding a common ion into the solution simplifies the problem, because often we get to ignore quite a bit of it, and you might even be able to do it without a calculator. You probably will choose to still use one though.